All right, good morning, good morning. We are going to continue with our unit on work and energy. So, our last set of notes, we talked about what work is. All right, we talked about how work is whenever you apply a force to move something some distance. All right, we also talked about the relationship between work and kinetic energy. All right, remember that kinetic energy is the energy of motion. Well, today we're going to be talking about two different types of potential energy. All right, so there are tons and tons and tons more types of energy, but these are just the three types that we're going to be focusing on in this unit. All right, so you have seen kinetic and potential before. You have heard that kinetic energy is the energy in motion. All right, well, potential energy is stored energy. All right, so we're going to be talking about two different types, and it is still stored energy. And the stored energy that we are going to be talking about is going to be the result of either an object's position or its condition. All right, so you can kind of see down here the two different types. All right, so our first type that we're going to be talking about is something called gravitational potential energy. You will see us represent that as GPE. And then we have something called elastic potential energy, and that's going to be EPE. All right, so the first one, the one that you're probably more familiar with, is going to be gravitational potential energy. All right, so that's going to be our GPE. So I want you to change this definition. I changed it on the notes, but it apparently did not update. All right, so I want you to change this. So gravitational potential energy is the energy an object possesses due to its position in a gravitational field. It's the energy an object possesses due to its position in a gravitational field. All right, replay that as many times as you need in order to rewrite that. All right, so it has to do with how far or how high above some point an object is. All right, so our equation for gravitational potential energy is mgh. So m is mass, g is acceleration due to gravity, and h is height. All right, so we should recognize this mg. We've seen that a ton of times before, so we know that Fg is equal to mg. All right, so we know that Fg, force of gravity, is another name for weight. So if I'm given the weight of something, I can multiply it by its height and get my gravitational potential energy. All right, so what we have to remember is that the gravitational potential energy is the work done against gravity to place an object at a certain height. And the higher the object is, the more gravitational potential energy it has. All right, now we will be talking about something called a zero level or a reference level, and that's going to change with every problem. All right, 9 times out of 10, your zero level is going to be the ground. All right, but it doesn't have to be. So you could say that you went from this branch up here to this branch down here. All right, so this would be your zero or your reference level. All right, but it could also be from this highest branch to the ground. So like I said, 99.9% of the time, our zero level is going to be our ground, but it doesn't have to be. It can change with the problem. All right, so let's try an example. We have Lassie, the 20-kilogram astro dog, is taken to a new planet. On this planet, she has 450 joules of potential energy when she is 8 meters above the surface of the planet. I want to know what is the acceleration due to gravity on this planet. All right, we always start off by writing down our givens. So our first given is Lassie's mass. So we know that she is 20 kilograms. Our second given is potential energy, and we know that this is gravitational potential energy because she is at some height above the surface of the planet. All right, so we have GPE is 450 joules. And then last, we were told that she was 8 meters above the surface, so that's our height. Well, I asked you to find the acceleration due to gravity on this planet, so we know we're looking for G. G is acceleration due to gravity. All right, we know that our gravitational potential energy is equal to mass times acceleration due to gravity times height. I'm looking for G, so I can divide both sides by mh. Okay, so we know that our acceleration due to gravity is our GPE divided by mass times height. Now, remember, we have multiple things in the denominator. There's no getting around this one like we did the other day. All right, so we have to remember to put parentheses around those two variables. All right, so we now can plug in our numbers and go. So we have 450 divided by 20 times 8. So whenever we plug that in, we do get an acceleration due to gravity of 2.81 meters per second squared. All right, remember that acceleration is a vector quantity, and acceleration due to gravity is always going to be negative because it's pulling it down. All right, so easy peasy lemon squeezy. So it's just mgh. All right, and again, the higher the object is, the more GPA or GPE it's going to have, the more gravitational potential energy it's going to have. All right, now our second type of elastic potential energy, or our second type of potential energy, is elastic potential energy. So it's EPE. So we have GPE and EPE. All right, and that's going to be the energy stored in elastic materials. So things like springs, coils, rubber bands, trampolines, things like that, whenever they are either stretched or compressed. All right, so we have a couple of new things here. So our equation for this is going to be 1/2 kx squared. All right, that is very similar to our kinetic energy equation. So remember, kinetic energy is 1/2 mv squared. So it does look similar to that, but we have two different variables. All right, for K, we have never seen K before ever. All right, K is going to be our spring constant. We're going to be talking more about what the spring constant is next week. But for right now, we just need to know that our spring constant tells us how stiff or how flimsy an individual spring is. I don't love that they call this a spring constant because it is not a constant the way we think. All right, we know that G is negative 9.81. That's a constant. We know that the speed of light is 3 times 10 to the 8th meters per second. That's a constant. All right, so this is not necessarily a constant like that. That just tells us that for that particular spring, it tells us how stiff or how flimsy it is. And the unit for that you might recognize is a Newton per meter. It's newtons per meter. All right, so the X is our third type of distance variable. All right, the X represents how far something has been stretched or compressed. So it's going to be found in meters. All All right, so let's look at this example. All right, so we have a slingshot is stretched 0.25 meters. If the spring constant of the slingshot is 80 newtons per meter, how much energy does the slingshot store? All right, so we have stored energy, we have potential energy. Because it has been stretched, we know this is elastic potential energy. All right, so we're going to be writing down our givens first and foremost. All right, so we were told how much it's stretched. All right, so again, as of right now, we have work is equal to force times distance. Okay, that was our first distance. We just got another one with gravitational potential energy. That was mgh. All right, now we have elastic potential energy, which has X in it. All right, so all of those are going to be distances. They're all going to be found in meters. So you have to figure out which one we are looking at. So we know that this is how far something was stretched. So we know it is X, and that's going to be 0.25 meters. All right, we were told that the spring constant, which is K, is 80 newtons per meter. And we want to know how much energy does it store. All right, so again, we are looking for EPE. So we know that EPE is equal to 1/2 of our spring constant times our distance stretched squared. We have both of those. We do not have to rearrange for this one. So that's going to be 1/2 of 80 times 0.25 squared. All right, as always, we are going to remember our order of operations. So you are going to plug in that 0.25 squared first, press equals, and then multiply it by 1/2 of 80. Which is 40. All right, so whenever you get that, you are going to get 2.5 joules. 2.5 joules. So as you pulled that slingshot back, you gave that slingshot 2.5 joules of stored energy. All right, so this is bringing it back. Remember on our last set of notes, whenever we were talking about the relationship between work and energy, work is what causes a change in energy. So think about that slingshot. We had to input work in order to pull it back, which gave it that elastic potential energy, which gave it the energy that was stored. Here, if we have 25 joules of work are done to lift a gold bar into the air, how much energy does the bar now have? It has that same amount of energy, 25 joules of gravitational potential energy now. Again, if you are inputting work that is causing a change in energy. So it did not have potential energy at the bottom, but as you lifted it up, you were giving it gravitational potential energy. And so the amount of work done is equal to that change in energy. All right, so our last example that we have today, all right, we have a spring launched a box of miniature horses 10 meters into the air. We know that the mass of the box is 250 kilograms. The first thing that I want to know is how much gravitational potential energy it has at its peak, so 10 meters into the air. We know that GPE is mgh. We were given the mass, that's 250. We know that G is negative 9.81. We're just going to use that 9.81 because we know that energy is a scalar quantity. And we know that the height at its peak is 10 meters. So we plug all of that in, and we know that that gives us 24,525 joules of gravitational potential energy. All right, well, where did that box get all of that potential energy? All right, and it came from the spring. All right, the spring did work to launch the box of horses into the air. All right, well, how much work did that spring do on the box? Okay, it did the same amount of work that energy had at the very top. So even if we didn't just write 24,525 joules, even if we know it wasn't equal, we know that we had I'm sorry, pause. Words are hard right now. All right, so we know that the net work done on an object causes a change in energy. Well, for this one, for our work kinetic energy theorem, it was work is equal to the change in kinetic energy. Well, it's the same thing with all types of energy. All right, because work causes a change in energy, we know that the net work done is equal to that change in gravitational potential energy. All right, because we were told that the box started from ground level, that tells us that the initial GPE is going to be 0. All right, because it was not at some height. Height was 0. There was no gravitational potential energy at the bottom. All right, so that means that we have our final GPE minus our initial GPE, excuse me. So that means that we have 24,525, which is what we just found, minus 0, which gives us 24,525 joules of work. All right, so those are the things that we need to keep in mind. Now, the very last thing that I want to show you is looking at the units. All right, so we learned in our forces unit that force is equal to mass times acceleration. All right, well, that helped us to see what a Newton was derived from. So we know that a Newton is the same thing as a kilogram meter per second squared. All right, so we know that work is equal to force times distance. We know that work is measured in joules and that joules can be broken down into a Newton meter. All right, well, we know that a Newton is a kilogram meter per second squared times meter. All right, so all of that is the same. A joule is equal to all of that. All right, well, whenever we started talking about kinetic energy, all right, so we saw that kinetic energy is 1/2 mv squared. So that's a kilogram. Velocity is meters per second. So we have meters squared per second squared because we squared it. So say we factor out one of those meters. All right, we have a kilogram meter per second squared times a meter. Well, what do we know that a kilogram meter per second squared is? We know that's a Newton. So we have a Newton meter. So that's the same thing as a joule. So kinetic energy is measured in joules. All right, what about GPE? All right, GPE is mgh. Mass is measured in kilograms. G is acceleration due to gravity, so that's meters per second squared. And then height is measured in meters. So once again, we have a kilogram meter per second squared, so that is a Newton meter, which is the same thing as a joule. So GPE is also found in joules. Well, what about EPE? All right, EPE is 1/2 kx squared. So K, we know, was a Newton per meter, excuse me, and X is a distance, which is meters squared. All right, well, we have meters on top, meters on bottom, so that's going to get rid of one of those meters. So that's going to be Newton meter. Hey, that's a joule too. All right, so all of this is showing that work, kinetic energy, GPE, so our gravitational potential energy, and elastic potential energy are all measured in joules, and they are all scalar quantities. All right, so I just wanted to throw that out there so you knew why all of them were measured in joules, not just because work and energy go hand in hand. All right, and as always, if you have any questions or need any help, you know where to find me.